welcome back to Luke's Math. Today we're going to be talking about a brief introduction of how to count things. So this is really combinatorics essentially. We're going to be focusing more on ways to count number of things, as opposed to its applications to probability. That's why this is a part one. We'll save the probability applications for the next video tomorrow. But first, let's start with where we left off with the exercise. So for the first one, we assumed that they were mutually exclusive, right? We had that the probability of A is 1/3, the probability of B is 1/4, the probability of C is 1/5. And for the first part, we assumed that they were mutually exclusive. So that means they're completely partitioned sets. They're distinct. There's no overlap. So like when we're drawing like a Venn diagram, it's not really a Venn diagram because there's no overlap. So in this case, when we are looking for the probability of the union of all sets, well, that's just equal to the sum of each elementary probability. So this would be 1/3 plus 1/4 plus 1/5, which is equal to 47/60. Okay, now for B, it asks, what about if these are independent events? So independent doesn't mean mutually exclusive. They're two different things, right? So it just means if they're independent, then the probability that the intersection is just equal to the product of the two individual probabilities, or 3, right? But they're all independent. So any two events that you choose, they're independent. All 3 events are also independent. So to find this, we use the formula for the probability of the union. It's the really long one. And then we subtract the two combinations, so A and B minus A and C minus B and C, and then we add on the intersection between all 3 events. Okay. But remember, what's important to realize is that any intersection is just the product between the events. So we can write it as the probability of A plus the probability of B plus the probability of C minus the probability of A times the probability of B. And then we can keep going. I don't want to have to write it all out. So what is this going to look like? This is 1/3 plus 1/4 plus 1/5 minus, now probability of A times probability of B, so 1/3 times 1/4 minus A times C, so 1/3 times 1/5 minus B times C, so 1/4 times 1/5. That's bad. And then minus all 3 multiplied together, so minus 1/3 times 1/4 times 1/5. And so that's going to result in, if you do the calculations, that should work itself out to 3/5. Okay, so there we go. All right, let's get started with introduction to combinatorics. The first thing that's usually discussed when talking about combinatorics is the multiplication rule. So what is the multiplication rule? Some of you might already have an intuitive sense for how this works, but it's still important to write out. So let's say there are n possible outcomes. So if there capital N possible are trials we're going to be conducting. Then what the multiplication rule says, that there are capital N to the R power of possible outcomes in the sample space. Okay. What does that mean? Well, it maybe sound more complicated than it actually is. Let's do some examples so you guys get a sense of what's going on here. The most common examples you'll see are passwords and license plates for this. So let's start with a password. We're looking for a password. We want it to be only letters, no numbers involved or special characters. And it's a 6-character password. Okay, and we'll say that it's, just for the sake of this problem, we'll say it's like not case sensitive. So we have 6 different spots to fill in our password, right? We're going to look at the different number of outcomes, I guess you can think about it, or for each of the possible 6 spots. So for the first spot, how many different ways or how many different things can I put in that first spot? Well, there's 26 letters, right? So there's only 26 options. How about for 2? I can repeat. There's nothing that's stopping me from repeating, right? So there's still another 26. 26 for the third slot, 26 possible letters for the fourth, and so on. We have 26 different possible outcomes for each spot in the password. So what we're saying is how many outcomes in total for this password. But what would happen is by the multiplication rule, we multiply these together. So it'd be 26 times 26, do that 6 times, which is where the formula comes in, 26 to the 6th power. So 26 in this case is our n, which is our possible outcomes, 26 different outcomes, and 6 is the number of trials. Right, we're doing it 6 times. Okay, what if we don't have 26 for all of this case, right? So like, what about for a license plate? Specifically, we'll say this is a California license plate. Okay, for those of you who don't know, California license plates have 7 characters. And so for the first one, it's a number, followed by a letter, followed by a letter, followed by a letter, and then the last 3 are numbers. So we're going to look at how many different ways are there to construct a California license plate. Well, there are 10 different numbers to choose from, right? 0 through 9, that's 10. For the letters, 26. Cases don't matter. I guess maybe you could make a distinction. I don't know if they would allow like a... There's got to be some sort of rule with an O and 0, right? Because how do you just tell that between those two? For this case, we're not going to care. 26 letters for the second one, because we can repeat, why not? 26 letters for the third, and then lastly 10 for each of the numbers. So by the multiplication rule, what this says is we'll have 26 to the third times 10 to the fourth. For the multiplication rule, we like to multiply them all together. Okay. One more example, still with the multiplication rule. This is a pretty classic combinatorics result, and it's still very important, even though it's not, I don't know if it's necessarily going to be super important for what we're doing with mathematical statistics, but we can also use the multiplication principle to look at subsets of a set with m elements. So take a set with m number of elements. How many possible subsets are there? Some of you might already know the answer to that question, but how do we figure out how many possible subsets can be formed? Okay. So, well, let's think about it. Is there a way in which we can find it? The way most people sort of go about thinking about this is, let's go through every element of the set. So the first element, do we want to include that or not in our subset? Let's say we want to include it. Go to the second element. Do we want to include that or not include it? Keep going. The third one. Do we want to include that element or not include it? And we keep doing that with all elements of the set, right? And hopefully you can agree that if we do that with any set, we can describe any sort of subset with that method, right? The null set is a subset of every set. The way to get the null set would just be to not include everything in our set. If we wanted to get the set, we would just include everything again. So there are two number of outcomes, and there are m different trials for each element of the set. So there should be 2 to the m subsets in each case. Okay, try to convince yourself of that. Okay, let's move on past the multiplication rule. Next we have a theorem. And here we're going to talk about permutations. So this is sort of we're kind of defining it, but also this is a way to do the theorem. So the number of permutations of n distinct, that's the key word, they must be distinct objects, is n factorial. Okay, and the proof comes from just describing what a factorial really is. And for a refresher, n factorial is equal to n times all the natural numbers that come before it, so n minus 1, n minus 2, dot dot dot, times 2 times 1. So if it's 3 factorial, it'll be 3 times 2 times 1. Okay. So let's keep going. A permutation, what is a permutation for those of you who don't have an experience talking about it? Permutation is a distinct ordering of something, right? So if we have, like, let's say we have A, B, C. What is a permutation of that? It should be a rearrangement of those letters. So a permutation of A, B, C would be maybe B, A, C, or C, A, B in this case, right? And so how do we count the number of permutations? Well, let's see. How would we count the number of permutations of A, B, C? What can go in our first slot? How many letters are there to choose from? Well, in the first position, there are 3 different letters to choose from. I could put an A, I could put a B, or I could put a C in there. So 3 different options. How about for the second? Well, there should only be 2 left, right? Because we've chosen 1 for our first slot. So for the second slot, there should only be 2 left. And then how about for the third slot? There should only be 1, right? So there are 6, 3 times 2 times 1, distinct orders in which we can rearrange A, B, and C. So that's a way to think about permutations. Let's take it a step further. You guys might have seen this formula before, but we have that the number of permutations of n distinct objects, it's still permutations, so it still must be distinct objects, and that'll be relevant later when we talk about combinations. Taken, so in this case we're taking R from the list, so taking R number of objects at a time, then in that case, if we want to limit how much we're taking, we describe it, the number of permutations, as the notation is NPR, where N is the number of objects and R is how many we're taking. You can read it as N pick R or N permute R. The formula is N factorial over N minus R factorial. Okay, let's do an example to highlight what that necessarily means. So let's say we have 6 different characters that we are going to choose from. 1, 3, A, capital M, the @ sign, and a tilde. Okay, so there's 6 different objects. These are all distinct, right? No two of these are the same. And I want to look at how many distinct ways ways to arrange the characters. Let me read out the second one. We talked about this when we first introduced a permutation. This should just be 6 factorial, right? There's 6 in the first slot, 5 in the next, 4, 3, 2, 1. So 6 factorial. Okay. However, what if I wanted to make a 4-letter word? So I don't want all the characters, I just want a 4-letter word from it. How many distinct ways can I do that with no repeats? It's also worth noting that we're doing no repeats here. And this applies to both cases as well. So, well, the answer to this is the other theorem, right? Where 6 total distinct objects, we're going to pick 4, and we're looking at all the possible orderings, permutations that we have. So using the formula, it would be 6 factorial over 6 minus 4 factorial, which is equal to 6 factorial over 2 factorial, which would give us 6 times 5 times 4 times 3, or in this case, it's 360. Okay, but what's really going on here behind the scenes? Because I know the formula, but why is the formula working? Well, if we want 4-letter words, right, there's only 4 different trials you can think about. How many options are there for the first one? Well, we have any of the characters to choose from, so we have all 6 available to us. How about for the second one? There should be 1 missing, right? Let's say we take the 1, and there's only 5 left over. For the next one, should be 4. How about for the last one? 3. We're only choosing 4, so we're going to stop there. And so that's our permutation. It's 6 permute 4. Because we have 4 different number of trials, essentially. We're taking 4 characters at a time. Okay. The last thing we need to talk about is a theorem. These are combinations, which are very similar to permutations. So we say that the number of distinct, sorry, not distinct, my bad, I'm messing up the definition. Let's erase that. So the number of combinations of n distinct objects, distinct is also important here, right? Combinations and permutations, we're dealing with distinct objects. Chosen R at a time is, and here's the formula. The notation, sometimes you'll see it as n choose R. Other times you'll see it as sort of this parenthesis where the n is on top and the r is on the bottom. But the formula is described as n factorial over r factorial times n minus r factorial. Okay. So that's interesting results. Let's talk about some of the differences between these two. The main difference is order. So permutation is a reordering of things. A combination is we're selecting a group, but we don't care about the order. So let's see. With permutations, this is a little bit of a note. Let's say we had A, B, and C to choose from. We have three distinct objects. So we have distinct objects, meaning we can look at permutations and combinations. So in the case, if we care about order, right, well then what are the different orderings of A, B, and C? You can start with A, B, C. We can start with A, B, C. We could do A, C, B. We could do B, A, C. We could do B, C, A. We could do C, A, B. We could do C, B, A. So there's 6 different ways. Those are the permutations. Those are the order. With the combination, however, order doesn't matter. Right? So how many ways are there to choose from the 3 letters? If we want to choose all 3, there's only one way to do that, right? We have like a set of A, B, and C. A, B, C in a combination is not any different than B, A, C because we still are choosing all 3 letters. Now, if we wanted to choose 2, so like this is for if we were selecting 3. Now, let's say we wanted to select only 2. How many ways are there to select 2? Well, I can choose A, comma, B. I can choose A and C. Or I can choose B and C. Those are the only ways to do it, right? Because the order doesn't matter. So AB is different than BA. Isn't different. Did I say it's different? Sorry. AB's isn't different from BA when we're talking about combinations because we don't care about the order. We're just looked at what are we selecting. Okay. Yeah, don't worry if it doesn't make all sense right now. It takes a little bit and a lot of practice to get comfortable and familiar with, but next video we're going to talk about more of the applications with probability as well as go over more examples with combinations because combinations are the most important takeaway I think from this. So we didn't go over a lot of examples with combinations. We're saving that for tomorrow. That is the most important takeaway, is understanding how combinations work and how we're going to use them going forward. Okay? I'll see you all next video.